to be clear.
5 minutes.
It's 5 minutes long.
No.
I was thinking like it will be horrible.
Okay.
Okay, thank you.
Yes, please.
Sorry. Okay. Hello, everyone. My name is Jesse Volt. I'm a second-year PhD student at Gibwa University, and today I will talk to you about a project titled Plasmoid identification in 2D GRMHD simulation. These are still preliminary results, so they're still subject to change. But I would be happy to hear your feedback on it if you. Yes. Okay. So brief overview of my talk will be general introduction to the various things, including like what's the difference between ideal and resistive MHD. And then I will go into some details about my plasmoid identification algorithm, but not in too much detail. It's still unpublished work. And then I will conclude with a summary and output. So the overview of the setup. My GRMHD solver of choice is the black hole accretion code developed by Oliver Ford and extended and improved by Hector Levanos. And it does what all GRMHD codes do basically. So you start from an equilibrium torus, which is evolved till it's turbulent and we have a more physical realistic system. And I do this for MAD setup. So we have a resistive ideal and a resistive MAD setup. And in those setups, I will look for plasma. And at the moment, I only show results for the dipole. So a single dipole in field configuration, which we see here on the right. Check. This works nice. So it's just a single loop, dipole loop that's orbiting in the anti-clockwise direction, if I'm not mistaken. Hard to see now, but I use, like, we can already see Buck has a nice EMR feature. Okay, pointer stops working. But you can see the blocks are a different size, and I use a standard MKS, so 1.5 shield metric grid. So we have more resolution in the equatorial plane and close to the black hole. Yeah, so the primer on ideal versus resistive MHD. For ideal, it basically assumes for ideal, we basically assume perfect conductivity. So these both sides we have like the electric field in the fluid frame E dash, and for ideal we assume a resistivity of 0 basically, and therefore the electric field becomes the right quantity, which is shown there. So it's the minus V equals B. And this works perfectly well in large sections of the GRMHD domain. This is further denoted by the Lundquist number, which is a variation of the Reynolds number. And we have the typical length size of the system, the typical fluid velocity, the alpha velocity basically divided by resistivity, which is 0 in the ideal case. So we have basically an infinite Lundquist number, but this, as I said, it works perfectly well in most regions because we have a large size, large array size, astrophysical sizes are large, with fluid velocity close to the speed of light. Yeah, so it makes sense. And then we go to the resistive. So we add the resistivity because there are certain regions where it does not work well. And these are regions where we have a high gradient in magnetic field and therefore a high current density. And in these places, these regions, you have magnetic reconnection. And this is best probed with using a resistive approach to MHD. Just a side note, in ideal, maybe people think I've seen plasmoids in ideal simulations. And that makes sense because there is actually some resistivity in ideal, but that's purely numerical. It's not like gauged to some physical interpretation. Yeah, the way I like to explain what a plasmoid is this kind of toy setup. So there's a 2D Harris sheet setup, which has no magnetic field in the y direction except for small perturbation. Some magnetic field with a large gradient in the x direction. And from this, you can go back to your vector potential, which I will call flux function from now on. And this flux function I will use in my algorithm to identify plasmoids. So we have a single bar of density here, and hopefully my movie will start running now. Yes. Yes. Okay, cool. So now the simulation will start running, and we see it will start evolving, and at some point it will start forming a region here which has low density but high magnetic field, and then we can see it becomes plasmoid stable. We see these plasmoid forming here, and basically plasmoids are circular structures, circular magnetic field structures, and therefore they will pop up in the yes. So we have circular magnetic field structure, which basically means you have so this is representation in Vx and Vy field. What this circular look like. And the most interesting thing is that it will pop up as a local minima in your flux function. And that's what we use to identify plasmoid. And we can also see here that it actually has some density. So what does this look like in a highly turbulent disk structure? Looks like this. We can still see this nice local minima in our flux function. We have density with plasma beta, which is thermal pressure over the magnetic field pressure, magnetization, which would be E squared over rho, and synchrotron emission velocity, which is the same as Laporte used in the same code comparison. And because that's also what we're interested in. We're interested in where are the plasmoids, how do they evolve, and are they visible, which basically gaugeable with this quantity. And then mad disk does what a mad disk does. So at a certain point, it will stop accreting, which is also an artifact because it's highly confined simulation in 2D. In 3D, you're still expected to have expected to have accretion, that these kind of evacuated regions, these flux eruptions, are only fairly localized. So so this is for resistive. We saw a lot of features, and the same can be shown for ideal. And at some point in ideal, we see that the disk actually becomes less turbulent. It will have this slight intermittent period where it's fairly calm, and at some point it will start again due to some the stability is popping up. But I want to pay attention to that particular feature where you have kind of an over density going into, and that this produced this flux eruption from there, and we see some plasmoid stable or current sheet forming and some reconnection events there. Okay. Yes. So what does this look like? So this is my algorithm, which identifies these local minima, local maxima, and you can see that at the moment I have it like set up in a way that really focuses on these larger structures that keep on being there for a long time. But you also have some fairly transient features close to the black hole here. Those it catches left well, but like that's also a matter of like scale, because at the moment I'm looking these large scale things, and if I would zoom in and fine tune it there, I think it will have little problem to make it work there. Yes, but just a matter of what you're interested in. At the moment, we're interested in these greater features that kind of persist for a longer time. So what does this look like as a function of time? This is still quite preliminary and quite, as you can imagine, depending on the number of input parameters I give it. But at the moment, we see that the plasmoid for resistive case, the number of plasmoid for variable and slightly greater as well. But we also see here that this is, by the way, the average size of the plasmoid, because it's also fitted with the geometrical function to get some gauge on how big it is. You see, you have slightly more plasmoid, but also smaller in size. So there's actually some difference there. But as I said, it's still preliminary. We're still seeing how to improve this. I will already come to my summary, basically. Yeah, as I want to emphasize the preliminary work. Yeah, but at the moment we're well able to detect large field structures in the simulation. And at the moment, the conclusion is that this resistance setup is slightly more turbulent than the ideal one. I will investigate additional models, so I'll have new data set which has more higher cadence output. Yeah, as I said, like Plasmoid highly transient features that are, yeah, that can occur for a slight amount of time. So by having a fairly high output gain from 10M, which is kind of normal for zero simulations, we may miss some, and that's obviously not any. And the main thing is that we want to investigate it for different magnetic field configurations, so probable and so resolution tests are also important for resistive simulation. But I wanted to highlight like these features that remain there for a long time. They seem to be related to some kind of plasma instability driven inversion into this, which terminates at a certain point and forms this plasmoid. And this is something we want to look into more to better understand what's actually happening there. And the eventual goal will be to expand this to 3D, but the expectation there is obviously that the geometry will change very rapidly. We don't have this nice circularly confined structure there. You will have these flux rows. But we're also confident that by using some smart slicing procedure that we can still use this kind of simulation. My algorithm. We can just adapt my algorithm a bit and maybe optimize it. That will also be good, I think, to do this good. And that's my talk.
Yes, you mentioned about how to, when you show these zones or ellipsoids where you are identifying the plasma. But I don't remember if you mentioned what is it, but you are.
Yes, it's still something I'm working on, and I do not quite feel comfortable showing at the moment. So you will see it when I publish it.
So you said that it's how you have the best ones. Are there kind of part of the
Yes,
how would you?
the magnetization.
Yeah, and you said that the plasmoids, so they are also higher than the or is there a difference in implement for the plasmoids?
They are just disconnected from the global magnetic field structure. They're a remnant of the reconnection event, which basically means to have a violent recombination of field lines, which ends up in this circular expression. So you can almost see that these things that will end up being in this for a long time, they're almost unconnected. Like I believe the George will. Image, no, not yet. It's a 2D, so it will make sense to show. Yes.
Maybe a similar question. If you analyze the number of the faults divergent, once you or
You mean the quantities m dot and so on? Or
you show that there is
I don't think I completely understand you. You mean this more like
there.
Well, I was wondering, were there any like low picture? They call it some depends on the number of plasmoids. If they turn on ideal, turn on this, for instance,
like I think in general temperature wise it's not very different. I think it's yeah. I think that's the answer. It's like at least visually, I've not done a dedicated like in-depth test of this, averages and so on. At the moment, my feeling is the resistance is slightly more variable in general. At least for this particular simulation. Can very well be that's just one of the parameters I put it together, but it's quite more variable. But if I want to give a coherent answer, we do need to do a lot more simulations.
Thank you very much.
Thank you. And thank you to Yeti for the introduction, but I can speak. Yeah, the idea is from Plasmoid, in principle, because we are computing this electron temperature from this RV model, is that you don't know what is temperature. You know that you change the temperature from ions, and then you connect this temperature from ions to the electrons. But you still can modify this ratio in the electron temperature and ion temperature. It's not directly connected. But this is something that people is also doing in fixed rate. Okay. Officially, I can start. Okay. Well, sorry for people who are repeating my thought. It's basically the same that I was doing some days ago. And the idea is that I didn't want to present this in EHT because I assume that EHT people already know my work, but you are not. Yes. Okay.